And also I would like to call Professor Pankaj Konikar sir to come on the dais and to present the memento to Professor Vamsi.
So today we discuss about nano composites and its applications. So more about this one is how to evaluate the composite materials and what properties are useful for the composite materials in a particular applications. So this is the one actually what is a composite. So we know already the composite is nothing but a combination of different materials, right? So suppose if you take a steel or aluminum etc., we can say it is a metals. So because the material is same, but the composite is nothing but different materials. So what we can do is here we take some materials called as reinforcement, and we fill that reinforcement into the base metal. It may be material, not only metal, any of the other things. That is called as a matrix. So this is one example, like these are the reinforcement inside and this is the matrix, right? So maybe you can make a sandwich or burger or something, right? Similar to that. Why you are doing this? So if you eat a bread, the taste is different. That's why for maybe better taste we can add some other things, maybe fruit bread or like that, or sandwich like that. So same thing for a material. If you want the required properties for a particular application, then we add certain other materials which are having definite properties. So now this is what actually composition of the composites. Like we take the fibers or filaments as a reinforcement because these are having high strength, high stiffness and low density, and then we take a matrix material. So then here we take why matrix material is, it is also having low density but it has good shear properties. Then if you mix both, we get all the properties like high strength, high stiffness and better shear properties and low density. So to get the different combinations, we go for the composite materials, right? So we have so many applications nowadays. I think already in the previous lectures other speakers discussed about so many applications. So these are some of the mechanical applications, like we use as a turret shield or maybe industrial springs or maybe any of the medical tables where we can use in the scanning, and also bulletproof shields or maybe these wind turbines. Okay, not only that, many of the automobile industry applications also we use. So this is normally mostly nowadays we are using in the aerospace industry, automobile industry, as well as in the industrial applications like pipes, pressure vessels, or wherever we are storing the high pressure liquids or gases, etc. So then these are also different applications we use in the aerospace industry, like engine cowlings or maybe luggage racks or maybe even seats also made up of composite materials, or maybe boats or ships, and then this type of pipelines, etc. So back all these materials may not be having, may not be using the same composite materials. So normally we classify these composite materials as ceramics and metals and polymers. That is based on the base material, right? The reinforcement may be different. So now we see initially about the polymers, right? So here these polymers are maybe a compound of high molecular weight consisting of repeating units, and also these are normally a plastics. Actually we mix polymers with additives like thermosetting plastics and thermoplastics, right? So thermoplastics maybe we can recycle, but thermosetting plastics we cannot recycle, right? So these are normally polymers what we use in the preparation of composite materials, right? So here we have again the natural polymers are there, and then the elastomers are there, and synthetic polymers are there, right? So some of the materials like this silk or collagen or starch, like this, these are the natural polymers. And then we have the natural rubber or amorphous material or semi-crystalline materials. These are also called as elastomers. And we have thermoplastics and thermosetting plastics like polyethylene or polystyrene. These are the artificial polymers, right, or synthetic polymers. So then depends on our requirement, we use different reinforcement. Okay, so here if you take the matrix is a polymer matrix, like you take any of the polymer from the previous category, either natural or synthetic or elastomers, and then we add different particles. For example, here we are taking silica nanoparticles, and here we are taking carbon nanotubes, here we are taking quantum dots, and here we are taking the magnetic beds. That depends on our requirement, what application we want, or what are the properties we required for the composite material. Sometimes we required hardness, sometimes we required strength, sometimes we required lightweight, but we required impact strength. So depends on that one, we select our reinforcement material. For example, you take a cars, right? So nowadays maybe the front part and back part of the cars, that is what we can call it as bumpers, are made of polymers. Okay, so this bumper is actually like a protector, so it should have high impact strength, but at the same time it should have lightweight, because the mileage of the vehicle, it may be two-wheeler or four-wheeler or maybe anything, depends on the weight of the vehicle. So if you are able to reduce the weight of the vehicle, then you can get more mileage. But at the same time, if you reduce the weight of the vehicle, means you have to replace the metal parts with the lightweight materials. But if you are changing the metal part with some other polymer or any of the plastic, etc., then there is a chance of the damage, right? That means the safety may be decreased. That is why actually nowadays all the parts are not replacing with composite, but some of the parts where we can able to reduce the weight and not impacting the safety, those are replacing with the composite materials. Not only automobile, maybe in the aerospace industry also, right? So for example, you take this valve, so that is also made of composite materials, which acts as a soundproof, right? So if you want soundproof, what is required? That's what we can call that property. Pardon? Huh? Yes, damping property. So here the damping coefficient should be more, and it should absorb more energy but should not transfer to the other medium, right? So like that, depends on the applications, we select the nanoparticles and we reinforce the nanoparticles into the matrix, and then we manufacture the final component. So again here there are so many process are there to synthesize these polymer nanocomposites or hybrid nanocomposite. That means here also either you can reinforce one type of particles or more number of particles. That means you can mix two different types of particles, because some particles may be having high hardness and some particles may be having high ductility, right? So like that, depends on our requirement. We add either only one type of particles, maybe combination of two different types of particles, that we can call it as either nanocomposites or hybrid nanocomposites, right? So here this is like this, maybe this, if you see hybrid polymer nanocomposites, we can take a polymer and we can use some nanofillers, different two types, and then we mix it and we prepare the hybrid polymer nanocomposites like this. So what is the use of these nanocomposites? Why you are taking only nanoparticles? Why not microparticles? Because the same material, right? So hardness and all these things may be same. If you take for example silicon carbide, all of you know silicon carbide is a hard material. Even we use as a abrasive particle in many of the machining process, right? In the grinding or super finishing, etc. So what is happening is, this is a hard material. So you want to improve the hardness or strength of the material. Normally we reinforce SiC particles. But if you take SiC particle maybe in the 10 micrometers size or maybe 10 nanometer size, what is the difference? Both are SiC only, right? So then this comes into picture, the surface area. So if you take the same microparticle, you are making into number of particles into nano size, then the overall surface area is increasing. So because of increase in surface area, some of the properties may be improved. That means the load carrying capacity may be improved. So the overall load you are applying or whatever the bonding between the nanoparticles and the matrix, everything is going to improve. So this is significantly increases the enhancement of the material properties because of increase in the surface area. Maybe that depends on the applications, right? So sometimes some properties are required. So why we require this hybrid polymer nanocomposites, right? So we are talking about composite material, that is mixing different materials, and then within that nanocomposites, and again we are going to hybrid nanocomposite. That means we are changing the reinforcement particle size micro to nano, and then again we are mixing number of nanoparticles. Why we require that is to increase the strength and stiffness. So all of you know stiffness, that is resistance to deformation, right? So that is if you want to get high stiffness, then we required some type of particles, and if you want high strength, we required some type of particles. Like that, if you have two different materials which are having one is high strength and one is high stiffness, then we both mix it and make it as a hybrid composite. And also the resistance, that is resistance to impact or resistance to corrosion or resistance to wear, where we have sliding surfaces are there, like you take a brake, right? So we have a brake disc, so which is continuously in contact with the brake shoe, right? So there is more wear and tear. So what we can do is, if you want to improve the wear resistance, then we can go for this type of composite materials. And then the transparency. So sometimes you want to see what is other side, right? So these are sometimes we make it polymers as a transparent material, so that that is normally for transporting the food materials, right, and transporting some type of liquid, etc. We want to see what is inside, so that's why we go for transparency. And then recyclability. So these polymers, if you want to recycle, then we can go for this polymers. And then the flame resistance. So these are resistance to the burning also, right, flame. And also transport properties. So because of the lightweight and easy to handle, we can able to transport one place to the other place. Like that we have some added advantages with these polymers, and also we are improving the properties of these polymers with the addition of different nanoparticles or fillers or nanotubes, etc. Then we are going for hybrid polymer nanocomposites. So then these hybrid polymer nanocomposites we can able to manufacture by different process, like hydrothermal route or intercalation method or polymerization or sol gel process, or maybe direct mixing of polymers and nanofillers or nanotubes or whatever you require. So I am not going to the details of each process, depends on the matrix material, depends on the nanoparticles or fillers, whatever is good, then we select that method, because each method has its own advantages and limitations. So based on the literature we select which method is suitable for our material and also for our application, right. So sometimes we need to fabricate thin sheets, or sometimes we need to fabricate very thick slabs, like that, depends on the size and shape, depends on the materials, etc. We select the required process. So then here also this functionalization is required. What we discussed yesterday, the same thing, but depends on our requirement, the process may be slightly different. So sometimes we use the combination of H2SO4 and NH3, or sometimes we use some other chemicals where the requirement is same. So if nanoparticles are like this, the surface is clean, so that the bonding with the matrix material may not be good. So that is why, to improve the bonding, actually we make like this, that is the active sites will be there, so we can go for functionalization. That means these are acts as a bonds between the matrix material and the nanoparticles, right. So maybe sometimes we are going for coating, right. So do you know, maybe in the olden days, if you have a wall, directly on the wall we are going to paint, that is a rough surface. But nowadays what we are doing, on the wall initially we are going for putty and then painting. Why? Because to improve the smoothness. So that means the bonding between the paint and the cement is also good, but that finish is not there because of the more pores between the unfinished wall. So like this, that is the putty acts as a bond between the paint and the wall, right. And sometimes also we use some other materials between two materials to get the better bonding. So here also same thing, these active sites will be helpful to get the better bonding and better properties between the nanoparticles and the matrix material. That's why we go for the particle functionalization. Of course, not required every time, depends on the what type of nanoparticles we are using and what is the matrix material, right. So then after fabrication of these nanocomposites or hybrid nanocomposites, we have to check. Why? Because the properties of these nanocomposites or hybrid nanocomposites depends on so many factors, that is type of the nanoparticle, size of the nanoparticle, shape of the nanoparticle, and also what type of what process we are using for synthesizing, right, and also other conditions, like where we are manufacturing and at what conditions we are manufacturing, etc. So because of these things we need to understand after manufacturing whether the material is good or not. So like that, that is called as characterization. We see characterization. So normally we use SEM, that is scanning electron microscope, that is to observe how the nanoparticles are distributed in the matrix, right. So the uniform distribution is required. Suppose the uniform distribution is not there, somewhere the nanoparticles are very large and somewhere it is not good, then what will happen? The properties may not be uniform, right. So normally we try to eat curd rice. So you want to mix the salt. So if you are not mixing properly, what will happen? So some part of the rice may be more salty and some part not good. Like that same thing. Here what will happen is, if we don't ensure the uniform distribution of the particles, then what will happen is the properties are not uniform. So that somewhere the properties are not uniform, and then there may be a chance of failure, or there may be a chance of not getting the required properties throughout the material, throughout the application. That's why we need to ensure how the particles are distributed, how the bonding between the particles and the matrix is taking place, etc. We need to observe. So normally we use SEM, and also we use XRD, right. So which we can see what the crystallinity of the nanoparticles as well as crystal structure and lattice constants within the matrix and within the particle. So we need to understand each and everything. So we use XRD also, and we use FESEM, because normally SEM gives only on the surface, but FESEM we can able to observe inside the lattice also. That's why sometimes we use FESEM, that is it gives the topographical and elemental information, right. And then we also use AFM, that is atomic force microscopy. So this also gives topographical analysis as well as the layer depth, and also gives roughness values on the surface or wherever you want. So it doesn't mean that always we use all the things, depends on our requirement. Sometimes we use SEM, or sometimes we use AFM, like that, or maybe combination. So once we ensure that particle distribution is uniform and the properties what we required are achieving, then only we go for the application, right. So then this is also we can use Fourier transform infrared spectroscopy, right. So this also gives analysis about the bonding between the particles and the matrix, and also identifying the molecular components and structures inside the matrix, as well as it also useful to get insights of the overall material, where actually Fourier transform will be used for this analysis, right. That's why it is called as Fourier transform infrared spectroscopy, right. So then after ensuring the properties and from the characterization, then we can go for the testing, right. So then normally we whatever the properties we require, that properties we can test. So if you see, this is one example. If you see hardness, actually this is the neat epoxy, that is without mixing anything. This is a matrix material, and then here we are mixing the carbon nanotubes, and here we are mixing the nano diamonds, and that means these two are nano composites, and these three are hybrid nano composites. So if you see the hardness, right, so then the hardness values are like this. So here the hardness is high. So you may think that the hardness here is good, the hardness here is less, but why we are getting more hardness here? So that is because of the synergetic effect between the particles and the matrix. So sometimes the hybrid particles give more bonding and then more uniformity in the matrix material, so that we can get the more hardness, right. So here the increase in hardness is due to the incorporation of nano reinforcement, that is clearly visible from the comparison between the matrix and the nanocomposites or hybrid nanocomposites. And also the rise in hardness is due to the actually uniform dispersion of nanoparticles as well as the reduction of agglomeration. So if you go on increasing the percentage, there may be agglomeration, that is nanoparticles may not be uniformly distributed and the properties may not be uniformly there. Okay. So that at some part the hardness will be very high and at some part the hardness may be less. So we have to add the nanoparticles till you get the uniform distribution. Suppose you are not getting uniform distribution, you have to stop there. That is why we test with different weight percentage of the nanoparticles, whatever it may be. So sometimes depends on the matrix material and depends on the type of nanoparticles, the weight percentage is varying, right. And then if you see, this is the tensile strength for the same material, the tensile strength also improved with the hybrid nano composites, right, compared to the neat composite and compared to the nano composite. So this increase in tensile strength is also due to incorporation of this nano reinforcement, because what is happening is the increase in stiffness of the matrix and elastic modulus, right, which will improve the strength. So normally by mixing this we are able to improve the elastic modulus and also we are able to improve the stiffness of the overall composite material, then the tensile strength will be high. Of course the flexural strength also maybe improves and impact strength also maybe improves, but always may not be possible. That is why we have to test. Sometimes only we get tensile strength, sometimes we get both impact and tensile strength, sometimes we get flexural strength. That depends on the type of reinforcement, right. So here also if you see, the impact strength is improved up to certain extent and then decreased if you go on increasing the weight percentage of this hybrid nanocomposites. So here it is a mixture of graphene and MOS, right. So that is, graphene is nothing but one form of graphite, right. So here also the impact strength increased due to increase of dispersibility of reinforcement in the base material. That is what actually because of the carbon-carbon bonds and which the interfacial bonding is enhanced, so that the impact strength is good, right. So these are all just examples. What I am trying to explain is, whatever properties we require, based on that we select the reinforcements and based on that we try to add different weight percentages and we test up to what percentage we are getting improvement and then it go on deteriorates. So we have to find out the weight percentage where it is, and this is the flexural strength of another composite. Here also same, if you are taking different layers of composite with nanofillers and then comparing the micro and nano composites, we are getting different types of flexural strength. So wherever you are getting the maximum flexural strength, then we go for that composition or that percentage. So here also the same thing, increase in nanofillers because of the formation of the agglomeration of the nanofillers. If still you are increasing, maybe here and here, the flexural strength again reduced. So we have to select the optimum percentage. So then the friction coefficient. So here also same, normally by increasing the hardness and by increasing the wear resistance, we can able to reduce the coefficient of friction as well as we can able to reduce the wear rate, right. So then this also same, we can able to increase this one by adding the some of the nanoparticle. So if you observe here where the time is going on, the variation is also different. So initially it is more, but later it is stable and it is like this. So where the coefficient of friction is less, this blue color one is less, that is nothing but 0.4% of graphene and MOS, right. So that is what giving the less coefficient of friction. And then the wear rate. So where if you see, wear rate is high in the normal matrix material, but wear rate is decreasing here, maybe at 0.6% and 0.4%. So sometimes you want wear resistance as well as we want strength also. So maybe at 1% you get more strength, but maybe at other percentage you get more wear resistance. So we can see what is our requirement. You want strength, or you want hardness, or you want wear resistance. Based on that we select the percentage of nanoparticles and also the type of nanoparticles. Suppose you want both the properties, maybe we can go for the optimum value where we get both better, right? So then these are the want surface. So if you see, this surface is very rough after the wear test, and this surface is almost very smooth. That means here the wear is uniform and wear rate is less, right? So wear resistance is good. So this is what about polymer hybrid nanocomposites or nanocomposites. So that means here we are using the matrix material is a polymer, right? So then the reinforcement may be sometimes metals or non-metals, maybe some other natural fibers or natural materials, or sometimes the synthetic materials, etc. So depends on our requirement we select it, right? But maybe depends on our application. You can go through the literature and you select which is suitable, and maybe you can try the new ones also, right? And then similarly the metals also we are using in many applications, right? So for example, you take brake drums or brake discs, or some of the parts of aerospace industries, right? Somewhere we are using polymer matrix composites and somewhere we are using metal matrix composites. So here these are the metal matrix composites. It's nothing but again the matrix material is metal. Again the filler materials may be the particles or tubes or clays, etc. Whatever you want you can use it. So then this is actually the graphene nanoparticles in the aluminum matrix. So that is the dispersion where you can see after the synthesis. So here also same, we have normally if you take aluminum, mostly we use aluminum as a metal matrix in the composite materials, because aluminum has its properties, better properties like lightweight and high strength, etc. But at the same time the wear resistance may be less, right? And that's why we are going for the composites, or we are adding some other reinforcements in the aluminum matrix, right? So we have different series, 2 series, 3 series, 4 series, 5 series up to 8 series. So each series has its own significance. So depends on the application, we select the which series we want and which material we want. And then we know these are the different reinforcement particles in the literature. People used different reinforcements, and these are the basic properties of all these reinforcement, like density, the fracture toughness, and what is the structure, what is the hardness, melting point, and coefficient of thermal expansion, thermal conductivity, etc. So depends on our requirement, right? So if you are using for high temperature applications, then you can select the high melting point reinforcement, or if you want maybe more heat transfer, then we select the high thermal conductivity materials. Like that, depends on the application we select the reinforcement. So these are all the applications where we use metal matrix nanocomposites. So nowadays we are using all these things, like maybe the brake disc, or maybe in the railway sector also we are using this metal matrix composites, where the outside dome or outside parts of the engines or railway coaches we are using. You can see nowadays, right? And inside the coach, the inside material is almost the polymer matrix composites, whereas some of the outside parts are the metal matrix composites, right? So we are using these truck bodies, or maybe the trucks, and the piston rings or connecting rods or drive shafts, etc. So many applications are there we are using for this one, right? And these are the different fabrication techniques we use for the metal matrix nanocomposites or hybrid nanocomposites. That is, we have stir casting method, and we have spark plasma sintering, or compo casting method, or ball milling and hot isostatic pressing, then squeeze casting, and we have a powder metallurgy route, and then we have ultrasonic custard casting process, etc. So this stir casting and ultrasonic custard casting is nothing but similar to our basic casting process, but some advancements are there because we are mixing the nanoparticles or hybrid nanoparticles. So, but the basic procedure is the same. We can melt the metal and we mix the nanoparticles at some temperature, and we use ultrasonic vibrations to mix thoroughly like that. So then this is one example of hybrid nanocomposites which are fabricated from aluminum 6061 Li and SiC nanoparticles and graphite nanoparticles. Why SiC and graphite? So you know SiC is a hard particle, right? So which will improve the hardness as well as the strength of the materials. But at the same time I want more wear resistance. So graphite is again a lubricant, solid lubricant, what we discussed yesterday, right? So if I mix both nanoparticles, maybe I can get more strength, more hardness, at the same time I get more wear resistance, like by reducing the coefficient of friction the wear is less. So like that by combination, by taking the combination we can get the better properties. So this is actually the methodology to fabricate this hybrid nanometal matrix composites. So this is the setup. So we have a crucible and we have a furnace, and all this is the setup where we heat the metal in the crucible, and also we mix the nanoparticles with the help of the ultrasonic vibrations, right? Of course we need to follow certain formulas, and we have to calculate all these energy, what is the amount of energy required, what is the vibrations frequency required, etc., etc. And actually what will happen is, if you don't mix properly, then all the particles are like this at some place. So that's why we create vibrations, and also we give the shock waves like this, so that the dispersion will take place. Okay. So then finally the particles may be distributed because of this acoustic streaming, and we get a uniform distribution in this process, right? So this is the process used for manufacturing of this one. So this is the initial aluminum alloy, and this is SiC particles, and this is the graphite particles. So we can test the purity of this matrix as well as the nanoparticles separately by using XRD and other things. And then this is TEM analysis to check the composition of these particles or composition of the matrix as well as particle size, etc. So once you ensure the particles are in the nano level and then the purity is good, then we can go for the fabrication. So right, so these are the different specimens manufactured like this. So you may ask a question, why 2 weight percentage is fixed here? So this is again based on the literature and based on the initial experiment. Initially we prepared nanocomposites with aluminum 6061 Li mixing with SiC. So there we verified different weight percentage of SiC, maybe 0.5, 1, 1.5, 2, 2.53 like that, and then we got the optimum percentage is 2 weight percentage for this particular matrix material and for this SiC nanoparticles. where with this combination we got good properties. So then we fixed the percentage of 2% of SiC. Then the secondary reinforcement is introduced by varying the weight percentage of secondary reinforcement, that is the graphite. Okay. So the preliminary results are not presented here. Directly I am going to the hybrid nanocomposite. So the denotion, these composites are denoted like this. So these are the different specimens fabricated by this composition. Then this is the density verified. So what is happening? If you go on increasing this one, what is happening to the density? So normally the density is increased, right? So but at the same time with SiC the density is increasing, but with the graphite inclusion the density is slightly reducing, right? So because the weight of this nanographite is less, or density is less. And then this is the XRD analysis of all the specimens to ensure what is the composition of that material. That means during melting and fabrication any other elements are formed or any other reactions are there. To verify that one we do the XRD analysis, right? And then this is the optical microscopy analysis, like how the particle distribution is there and how the matrix and particles are distributed, and this is what the different composites, right? That is one is 2Nc and 0.5, 1, 1.5, 2 and 3%. And from this one we can able to understand the grain size. That means already we melted the Al6061 and mixing the nanoparticles and then solidifying. So the grain size is varying because the grain size in the original matrix is different, but now again you are going for casting process with the addition of different particles. So there is a variation in the grain size. So we see what is the grain size. So if you observe, the grain size is reducing, right? So the smaller grains will give better strength, right? And also will be normally the resistance to the other impact and other dislocations, etc. So like that this may be some advantage if the reduction in the particle size is, grain size is better, so that you can get the better properties, right? So then this is the SEM analysis. If you observe that one, if the nanoparticle percentage is increasing, then you can see the agglomerations, so that we can see this is clusters are there, here SiC clusters are there, and here also SiC clusters are there, and this is what the graphite, and this is the graphite, and this is the SiC. So based on the color and based on the size and morphology, we can identify whether the particle distribution is good or not. So then again, after checking the particle distribution and above 3% we are not able to fabricate, because after that the composite is not forming, that is the specimen is not good, because more agglomerations are there and there is no mixing of nanoparticles properly into the matrix. So that's why we stopped at 3%. So this is the hardness. So if you see, the 2Nc is having more hardness, and once you are increasing the graphite percentage, because SiC percentage is same, right? So once you add SiC to this matrix material, actually the hardness is improved, right? But again, if you are adding the secondary reinforcement, then the hardness is slightly reducing, okay? Because SiC, the properties are different, the graphite properties are different. So why we are going for this one is actually to get the combination of better strength, better hardness and wear resistance. So if you want to improve the wear resistance, or if you want to reduce the coefficient of friction, then we have to sacrifice some percentage of hardness or strength. So here if you observe, when the graphite is adding, slowly the hardness is reducing. So then the combined effect of reduction in the grain size as well as SiC particle agglomeration, particle strengthening effect, because of this one the hardness is slowly reducing, right? And then if you see, this is the tensile properties. The tensile properties also same. So if you see the ultimate tensile strength, so it is initially increased from matrix to the 2% of nanocomposite, and then in the hybrid nanocomposite it is slowly reducing, and this is the yield strength, and this is the percentage of elongation, right? So then this is the fractography of hybrid nanocomposite, that is once in the tensile test the fracture takes place, on the fracture specimen if you see how the nanoparticles are inside, this is nothing but a cross sectional view type, right? So you can see the particle distribution is like this. So we have different dendrites are there, micro cracks are there, some facets are there, so all these are there. So we can try to understand, we can try to analyze where the fracture is uniform, so where the fracture is better, right? So then based on this also we can come to some conclusions. So then this is based on the mechanical properties like hardness and strength, we come to some conclusion where the properties are good and where we can go for this one. So then these are the tribological properties, that means we are testing the wear properties, right? Coefficient of friction, right? Wear resistance, etc. Then you can see here, this is the wear rate, and on the load, if the load is increasing, normally wear rate is increases, obviously the same thing, if the load is high then the wear is more. But at the same time within the matrix or within the different composite materials, if you see the wear rate is less for the 2 HNC, that is at 2 weight percentage the wear rate is less, and again at 3 it is increasing. Why? Because of the agglomeration of the particles, maybe non-distribution of the particles, at some parts wear is high, at some parts wear is less, we do not have uniform wear. But in the 2 HNC there is nothing but at 2 weight percentage of SiC and 2 weight percentage of graphite we are getting the less wear rate, and this is wear rate at same load conditions, but this is at extreme high speed and high distance, this is low speed and low distance, right? Because these three are the variables, load, speed and distance. Distance is nothing but time, if you run more time the distance is more, right? So this is the lowest conditions and this is at highest conditions. So in both the cases we are getting 2 HNC is the better. So why it is happening is actually this is again because of the graphite which acts as a solid lubricant, so which gives wear resistance. At the same time the SiC is giving the more strength and hardness. So compared to the normal aluminum alloy, actually all the composites are having the better wear resistance. But at the same time within that, if you are increasing the graphite percentage, because of the self lubricating nature of the graphite, we get a better wear resistance, right? So then this is the same thing but with respect to sliding velocity. So this is with respect to load, this is with respect to sliding velocity, and then this is with respect to sliding distance. But in all the cases if the distance is more, that is nothing but if the time is more, the wear rate is increasing, and if the velocity is high then the wear rate is increasing, and the load is high then the wear rate is increasing. So if you are increasing the load or anything, but at the same time within that the 2 HNC is giving a better result, that is less wear rate compared to the other materials. So then if you see the wear coefficient, so then again the wear coefficient is reducing, right? So that with respect to the load, and this is for the material and this is for the sliding distance and sliding velocity. So when the material, if you take actually the wear coefficient is reducing, so that's why we required less wear coefficient. So we are going to fix with the 2 weight percentage of SiC and 2 weight percentage of graphite, which may be a better combination for this particular case study, not all the conditions. So this is the coefficient of friction. So coefficient of friction is also less at 2 weight percentage, right? So we see this one, and then again after 2 weight percentage again coefficient of friction is increasing. Why? Because that's what I told you, because of non-uniform distribution of graphite or maybe the agglomeration of SiC, what will happen is the surface is becoming rough, and which is giving the more coefficient of friction, right? So this is again the same thing, coefficient of friction with respect to sliding velocity, and it is coefficient of friction with respect to sliding distance. But in all the conditions, the coefficient of friction is less for 2 weight percentage of graphite, right? So that is for a combination of Al6061 with 2 weight percentage of nano SiC and 2 weight percentage of nano graphite, we got better results within these selected conditions. So then this is the worn surfaces in the SEM, right? So if you observe again the worn surfaces, you can understand the nature of this one. So here the surface is rough, and here also it is having. So this is a little bit uniform wear is there, and here again the wear is increasing. That's why the surface is more rough. Here also more rough, here also more rough. So compared to this one, we can understand why at 2 weight percentage the wear rate is less, why coefficient of friction is less. That we can able to correlate between the numerical values and the inside images, right? So this is also worn surfaces at different loads and different speeds. So these are also same. So in all these conditions we are changing the loads and speeds. So this is also same at 20 newtons load and at higher extreme conditions. So then this is again EDX analysis. So after the worn surfaces, and if you take the wear debris and if you do again the EDX analysis, if you observe what is there in the debris, that is whether more SiC is there or more aluminum is there or more graphite is there, and how the wear is going on, that we can able to understand from the wear debris, right? So this is again the wear debris analysis. So you see the wear debris at a different conditions. This is for Li, this is for nanocomposite, and this is for hybrid nanocomposite. So if you observe, this is more uniform wear debris, so that the wear is uniform and the wear rate is less and the coefficient of friction is less, right? So this is also analysis of wear debris, EDX analysis, and this is the wear mechanisms. That is you see this one with the load and the sliding velocity, that is within this region. Actually what is happening is the wear mechanism is we have a graphite thin layer and smaller size oxide debris are there. But if you are increasing the load in the same condition, in the same at the same velocity, if you increase the load, then this is the region where we get smaller delaminations are there and graphite thin layer is there, and the medium size oxide debris are there. Like that, if you take any particular value of velocity and load at that particular point, you can see the region, depends on the region, you can get what type of wear is there. That this analysis is from the wear debris. At different conditions we collected wear debris, and depends on the XRD analysis and SEM analysis, we mapped this one like that. Suppose you take the high sliding velocity, maybe 2 meter per second, and load also maybe 25 newtons or 30 newtons, then the region may be F. That means we are getting a severe abrasion wear and also higher depth of penetration is there. Why? Because actually at that load and at that highest velocities, actually whatever the composite material, that is not able to give more resistance, right? So like that we can understand this one from the analysis of where debris or worn out surfaces, right? So this is the overall summary, right? So what you understand from this one, so we have to select the base material, depends on our application, and we have to select the type of nanoparticles. It may be one nanoparticle or two different types of nanoparticles. So if I want more strength and more wear resistance, I need to take two different nanoparticles. Then we have to mix this one and we have to select the proper synthesis methodology, right, or fabrication technique. Okay, so because all fabrication techniques may not be suitable for all the materials, depends on the size, depends on the shape, etc. Then at a different nanoparticle percentages, different size of nanoparticle, different shape of nanoparticles, etc. Then we have to try, we have to select, we have to test it where you are getting the better mechanical properties and better tribological properties. This is a common procedure we followed, but depends on your application. Suppose you want only wear resistance, then maybe you can go for only graphite. If you don't require strength, then only you required this one. Maybe you can add only graphite or MOS2, so that acts as a lubricant and wear resistance may be better, but at the same time the strength may be less. So like that, depends on our requirement, we select the combinations. We have lot of literature. So from the literature we try to understand which base materials are having which properties. Depends on application, we select the base material, and also we have so much of literature which nanoparticles are giving which properties, etc. Based on that, again we select the nanoparticles, and based on the base material, based on the nanoparticle size, shape and percentage, then we go for the fabrication technique and we evaluate the properties, and finally we go for the optimum percentage, so that we can use for a particular application. So the procedure is either it may be a polymer matrix materials composites, or maybe the metal matrix composites, same. But the fabrication techniques are different and the properties are different and our applications also different. So you select whatever you want, right? So this is about the nano composites and hybrid nano composite, both polymer matrix and metal matrix. Okay, any questions? So this is the general procedure we follow, and this is a particular case studies or applications. Maybe depends on your requirement, you can select your own based on the literature and you can try, right? Right. Thank you.